If no one, then I'll do my solution. And hopefully it's the right solution. Okay, whenever I start a problem solution, when I start out with my basic problem, I put down the information that I think I might need in the solution of the problem. In this case, we know beam 1 had a cross-section of 2 centimeters by 2 centimeters. It was made out of aluminum 1100, and we know whenever we talk about safety for a system, we need to know the yield strength for both plane stress and shear stress. So I got that out of the tables. And then I did the same thing for beam 2. This one is 4 centimeters by 4 centimeters. This one's aluminum 6061. And I put in the yield strength for both normal and shear stresses for this particular material. Okay. The next thing I ask you to do is to draw a complete free body diagram. So we're going to sketch the member. We draw in any given forces, moments, torques, couples. The only thing we have is this one. $14,000 Newton force acting down. We then to see what we have for attachment points. We have 2. We have 1 at the wire. And we have 1 at the wall. we know that whatever we have to add for forces, moments, torques, couples using the equilibrium equations, we can only add them at attachment points for the two. When you look at this, when you look at the wire has to be pulling up in this direction. If it wasn't, this whole thing would rotate around this hinge and collapse back against the wall. So we know that this force, this is the overall force in the wire. It is acting down the wire. In fact, the wire is in tension. But we know we can break that down into its component parts. This is F wire X. This is F wire Y. And we know that that angle was 40 degrees. If we look at this attachment point, if we have this force in the wire here, this force wire X has to be going in that direction, because this vector plus this vector have to equal that vector. So I'm going to guess that this has to go this other way for F wall X. And then again, because of the tension of the wire, we expect that F wire Y is going to be going up. If we look at this, if this is going up, this is going down, we're going to have a force here in the Y direction. And we might want to guess that this would be going up, because if it wasn't, and you just had this one and this one, the thing would tend to rotate or sag counterclockwise. So those are sort of my guesses to start with. I then am going to go and use the 6 equilibrium equations. We know that for forces, we know the sum of forces in the X direction have to equal to 0. The sum of forces in the Y direction have to equal to 0. And the sum of forces in the Z direction have to equal to 0. Again, when I do it, I think of it very simplistically. This is the left have to equal the right. So in this case, F wall X has to exactly equal F wire X. One equation, two unknowns, we can't solve that. If we look at Y, sum of forces in the Y direction are going to be the ups have to equal the downs. What do we have for ups? We have this one and this one, so we have F wire Y plus F wall Y have to equal the downs. The only thing we have going down is the 1400. 14,000 newtons. So now we have two equations, but we have 1, 2, 3, 4 unknowns. That still doesn't do us any good. If we look at sum of forces in the Z direction, we don't have anything acting out of the board or into the board, so that's automatically satisfied. So the equations that we're interested in trying to utilize are these two, so we'll save those. What I'm going to do is go up here and erase this. And we know the next set of equilibrium equations we have are for moments. And we know we have 3 of those. Sum of moments around the x-axis have to be equal to 0. Sum of forces, sum of moments around the y-axis have to equal 0. Sum of moments around the z-axis have to equal 0. If we look at this, again, nothing is making this want to rotate around the x-axis. Nothing is making this rotate around the y-axis, so these are automatically satisfied. But if you look at this, there is something that makes this want to rotate around the z-axis coming out of the board. So we're going to look at sum of moments around the z-axis. We know that they must be equal to 0, and specifically know for directions that it has to, the clockwise have to equal the counterclockwise. And in order to apply this moment or utilize this, we have to pick a point in order to do that. And as we've stated before, you can take the moment anywhere you want to, but if you take it at an attachment point, you tend to help eliminate unknowns to make the problem solution easier. So if I call this point A, call this point B, I could take the sum of moments around the z-axis at point A, utilize that. I could take the sum of moments around the point B, around the z-axis, and do that. That would make the problem easier. I could pick a different point. I could pick it down here at point C. I could still do sum of moments around the z-axis at point C. I could get that, but then when I go to solve the solution, as we did the other day, you're going to have to use either substitution or addition subtraction, which is just more work for you to do. When I did my solution, I picked point A. So I said the sum of moments around the z-axis at point A have to equal 0. The clockwise still have to equal the counterclockwise. And whenever you take moments, you can do it however you want to. I would recommend that you put your finger where you're taking the moment, and then you look to see what each of the forces involved is doing. From where my finger is, F wall X, F wall Y, and F wire X all go through my finger. So when you look at the definition of a moment, it's a vector, which is a force times the perpendicular distance to the lever arm. There is no lever arm, so there's no moment contributions from F wire X, F wall X, or F wall Y. So the only two we have are this guy and this guy. So if I put my finger here, this one is going to make it want to go clockwise. So that's going to be 14,000 newtons. And the distance to that point is going to be 5 meters. 4 from here plus 1 more. That's the only thing that's making it go clockwise. For counterclockwise, we have this guy on the end, which is F Y or Y. And the distance there is a 4 times plus 6, which is 10 meters. And again, what we're doing is we're doing a perpendicular distance. So if I go across here, that is the perpendicular distance. When I consider this force, I'm going to here to get that perpendicular distance. Here I have one equation, one unknown. I can solve that. And if you do, F wire Y is equal to 7,000 newtons. So I can go back in and now substitute for that. If I go down here to my sum of forces in the y direction is equal to 0, and I know the F wall value was 7,000. Simple math, that means that, excuse me, I put that in my place. This is 7,000 newtons, then the wall has to be 7,000. So we can go back and make that substitution. Okay. Is that a complete free body diagram? No, because I still don't know what F wire X and F wall X are, so I need to solve those. We do know that they're equal, so I'm going to erase this part. And if we go back to the end and look at our original wire presentation, this is F wall Y, F wall X, and that angle was 40 degrees. We know this guy, it was 7,000 newtons. We're after this guy, so I can use a trig function. So we know the tangent of 40 has to equal the opposite over the adjacent. The opposite is 7,000. We can look up what the tangent of 40 is. So that makes f y or x to be 8,342.28 newtons. And again, if you rounded this off, that's fine. I didn't write that. So we can go back up and put those values in. We now have identified everything, so this is a complete free body diagram for this particular system. I then ask you, what about safety? For safety, we know we're always going to look at plane stress and shear stress. And by its definition, you know, the plane stress is equal to axial force divided by the area that's perpendicular to that axis. You know, shear stress is equal to shearing force divided by an area that is parallel to that axis. So we need to do a safety calculation whenever a force or an area or a material change. So if we look at our sketch, and this is beam 1, this is beam 2, and we look just at normal or plane stress for our system, we can see that for beam 1, plane stress for beam 1 is the axial force in beam 1 divided by the area that's perpendicular to that. The force we've said is the 8342.28 newtons. Our area is the 2 by 2 square centimeter. So I need to change that to meters to come up with our units of pascals. When I did that math, I had that value come out to be 20.85 megapascals. This value is less than the yield value, so we know that it is safe. Let's continue looking at just normal stress. If we go over to beam 2, we're going to have one calculation but we're going to have to look at it twice. So if I look at beam 2, hopefully you can see that in this beam 2, I still have the same axial force, but my area has changed to 4 centimeters by 4 centimeters. And I have that calculation come out to be 5.21 megapascals. So this is the plane or normal stress anywhere in beam 2. We know that its yield value is this. This is much less than that. So again, this is safe. Some people like to do a backup, and they might want to look at just what's going on in this little area there. You can do that, but you're going to come up with the same answer. Any questions so far on our free body diagram?
Professor,
yes.
For the second one for beam 2,
Yep.
I got 52.1, not 5.21. I don't know if I did it wrong.
Yeah, I got 52.1 too.
Okay. Do a quick calculation here. I could have written that down. I work out my solutions and then I rewrite them. So I've got okay. Okay, I'm still getting that. So this is this divided by 16 times 10 to the minus 4. 16 into this I have is 521.39. But then this division of 10 to the minus 4th becomes 10 to the 4th. And then if I move this 2 decimal places to make this mega, I get 5.21 times 10 to the 6th, or 2.51 megapascals. So I'm sticking with my answer. Anybody else? Anybody else get mine?
I also
Okay.
got 5.21.
Thank you.
Same here.
Okay, thank you. Okay, any questions on what we've done thus far for finding a free body diagram? And again, I always recommend that you list, before you even start the problem, what the various yield values are, things of interest, because you know you're going to be going back to look at those to compare safety. So if there's nothing else, what I want to do now is go and do shear stress, and I'm going to erase this. Erase this. Okay. I'm going to go back to my original free body diagram, and I know that the definition of shear stress is shear force divided by area parallel to that. You can use both vector quantities. So when I look at this, I have 1, 2, 3 shearing forces. A shearing force means a force in the y direction. So I know as I go across here, I'm going to have an interaction due to this shearing force. Then once I get past that one, I'm going to have another interaction here because of this shearing force. But when I look at this, I'm going to have a shearing force in that region where safety is going to be dictated by the aluminum 1100. I'm going to have a shearing force in this little region that's going to be dictated by this beam 2 yield value. And then finally, out at the end, I'm going to have another region where I'm going to have to do a calculation. And in order to find out what to use for the value for shearing force when you're doing this calculation, we need to do free body diagrams of what's happening as we move across. So let's cut beam 1 anywhere just to the right of where this shearing force is, just to the left of where it intersects with beam 2. If we make that cut and we look at the left-hand side, and here I'm looking at the left-hand side, so I sketch in all given forces, moments, torques, couples. How many given forces, moments, torques, couples do I have? Anybody?
1.
No. I have 2. I have this guy and I have this guy. If I look at my attachment point, and I want to do my free body diagram, I know I have to do this. And if this guy is going up, this guy has to be going down. It also has in it a moment, because if you look at this, if this just stays as is, this one and this one make this member want to rotate clockwise. But we're really not worried about the moment right now. What I'm interested in is that shearing force. So for this left-hand side, for beam 1, we're looking at the shearing force divided by the area that's parallel to it. That shearing force is 7,000 newtons. The area is, again, my 2 centimeters that I'm going to make to meters. And I had that value come out to be 17.5 megapascals. This is the shear stress in beam 1. We know that this value is less than this value, so this is safe. Since we've changed areas here, we should also really look at this little segment here. And if we do that, I want to cut this anywhere just to the right of the intersection between the two beams, just to the left of where this new shearing force is. And I'm going to look at this. So I've sketched a member, and this is the left-hand side. So this is the left-hand side. What I have for given forces, moments, torques, couples, I still have my 2. I have 1 attachment point. So again, if I put them back in, I'll put this one in just for completeness. But we're not worried about actual forces, we're worried about shearing forces. And this is again 7,000 newtons. So for this region, we know that tau xy in this little region here is equal to shearing force divided by the area. Shearing force is again 7,000 newtons, but my area has now gone to 4 by 4. And I had that value come out to be 4.38 megapascals. This value for shearing is less than this value, so this again is safe.
Can I interrupt for two questions?
Sure.
Do you want a free body diagram done for each section that we're calculating, or can we just do the calculations?
You can, well, that's, since I give partial credit if you miss something, I think you're better off drawing the free body diagram, just a quick sketch, to show me where you're coming up with the numbers that you use. Let's say you didn't do my little sketch, and somehow you decided that this value was 10,000 newtons. If I don't know where you got that number from, and it's wrong, it's hard for me to give you any partial credit because I don't know what you're doing to come up with that number. If you do it over here, and you inadvertently say that this is 10,000, that was just a mental lapse. I know where you got it from. I'll take off a very little bit here, but I won't take anything else off as you work through the problem.
Okay. My next question, the other question is, we'll have a shearing force on the aluminum 1100.
Yes.
That we have to calculate in the 14,000 newtons for as well. Is that correct? Where the two beams connect?
In other words, is there a shearing force right here? Yes. If you drew this right along the line, the intersection between beam 1 and beam 2, if you drew a free body diagram that was just, so this was exactly what, 4 meters long? Yes, there would be a shearing force right there, but you're going to have one value for shear stress on one side, one shear stress on the other side because of the change in area.
Okay, so I have to subtract the 1 meter distance on the 14,000 newtons, which is,
well,
to get it to the edge.
When you do the calculation for shear stress for beam 1, by cutting it anywhere just to the right of here, just to the left of this intersection, anywhere that's in here will have that exact same value that we calculated. When you go beyond that point and you do this calculation, anything you come up with there is going to be good. For anything in that region, just to the right of the intersection, just to the left of this shearing force.
Professor, when I did these calculations, I split it up and I did beam 1 and I kind of split it where it got wider and
Yes,
took
that's
the
fine.
beam 1 as the left-hand side and took beam 2 as the right-hand side. I didn't make quite the cut that you did there. I
So
cut
you
it
cut
right
it
in
here?
half, right where your hand is.
Okay. The only reason that worked in this particular instance, and you're gonna turn, as it turns out, you're gonna get the right answer, but the only reason you got the right answer is because this shearing force exactly matched that shearing force. If these two would have been different, you would not have been able to do what you did and come up with a correct answer. I'll look at a little version of this at the end to try to maybe better address that. Any other questions on what we did so far? When you did the original free body diagram? Yep. It's before the wall. You do not include the wall. Include the wall? And the answer to that is yes, there is, but it's a cantilever beams, and we're going to come into that later in the semester. Okay? Okay? You could remember what, I'm going to erase this over here just a second. I want to go back and sort of re-emphasize something. Maybe I didn't re-emphasize or emphasize it enough. But when we did our free body diagram, shorten up this a little bit. Okay. Okay, this was our original free body diagram. The beauty about having a free body diagram is you can cut it anywhere and still look at whatever section of interest you might be interested in and draw a free body diagram of that to see what's happening. So for example, if you somehow wanted to look at I'm going to make two cuts. I'm going to make one anywhere where you talked about halfway. So if we make this halfway for beam 1 and we make this halfway to beam 2, can I do that and analyze what's going on? You bet. If I want to see what's going on in this middle section, I sketch the member. And then I look to see what's going on. in this particular case, when you cut it like this, the only thing you see is this one force coming down. You have two attachment points. We have one for the cut here and one for the cut here. So this turns out to be an indeterminate problem. You can't readily solve this from the way you've cut it. You typically have to you have to go to where you have more information available to do that, and then you can go from there. But wherever you do cut it, you can use equilibrium equations to make it work. And then when you go to, again, when we did this left-hand side, if I went and did the right-hand side, so I'm going back here to where I cut it. This is the left-hand side. This is the right-hand side. If I do a free body diagram for the right-hand side, I sketch in any given forces, moments, torques, couples. So I have those two. I have one attachment point. And again, that's anywhere just to the right of here, just to the left of there. So I'll put this in just for completeness, although we're not going to use it. So if I went to find the shear stress in this region, we know shear stress is equal to shear force divided by the area parallel to it. So my shear force is 7,000. My area is still the 4x4. And I'm going to come up with the same value. Notice, if you look at what's going on here with the right-hand side, you look at what's going on here with the left-hand side. If you take the left-hand side and the right-hand side and you marry them back together to come up with the original number, this cancels with this cancels with this. And you don't have anything here. You just go back to your original free body diagram. That's the nice thing about doing these, is when you've done them, you always have a check and balance. All the solutions that I've done with you so far, we have started by taking this and starting at the left-hand attachment, work our way all the way across. We could just as easily have started on the right-hand side, make the cuts, and work our way back to the left. We're still going to get the same values. You're still going to be able to calculate the stresses, strains, whatever that you need to do. Did I answer your question, or I talk around it? Alicia, did that answer your question? Okay. Okay. So when we cut this and we use this shearing force, we're going to come up with the same answer we did before, which was 4 point. And this again was safe for shear stress in bar 2. And that was the basic part of the quiz. Anybody have any questions on that? Hopefully everybody now feels comfortable drawing free body diagrams. And you know how to do safety calculations for plane stress and shear stress. Again, you always have to do one if you change a material, if you change an axial force, if you change a shearing force, or if you change a cross-sectional area. You always have to do another calculation to come up with safety. So if I give you a quiz exam or whatever, let's say you calculated this first section, and let's say you made a math mistake, and you came out where this region you said fails. Whenever you do a quiz or exam with me, I still want you to carry on and do the rest of the calculations just to show me that you know how to do them and why you're doing them. Because if you've made a mistake here, I'll take off for that. But even though the rest of what you're doing is based on a mistake here, as long as you've done the rest of it correctly, even though you're coming up with incorrect numbers, I'm not going to take anything off. But if you say it fails here and it doesn't, and then you say, I'm not going to calculate the rest of them because it's failed here, and it didn't, then you haven't done this, and I will take off for that. Any questions on the basic part of the quiz? Okay. Let's look at the extra credit. Question? Yes. Whoop, somebody said something to me, but the little bubble evaporated by the time I got back. Did you resend that? Or just, okay. No, you can't really infer that. You really have to do those calculations. Okay, the next part I asked you was, what is the minimum radius to make the wire safe? So if we go back and we looked at our free body diagram, we had our wire going up at 40 degrees. This is the wire, and we know it has an X component and it has a Y component. If we look at just the wire itself and we do a complete free body diagram of the wire, what do? We sketch the wire. We know that we have two attachment points, where it attaches to the beam and where it attaches to the wall. And when you look at that, hopefully you can see that it has to be in tension in order to hold up the end of the beam. If this thing was not pulling up in this direction, then this would collapse back against the wall. So I've drawn my wire. I know that the force in the wire has to be that way because it's in tension. If I look at F wire X, F wire Y to come up with the force in the wire, I can use the Pythagorean theorem where force in the wire is equal to the square root of F wire X squared plus F wire Y squared. And I had those values to be because this guy was so when I did that math, I had the force of the wire come out to be 10,890 newtons. So if I put this in, if I do, I don't really need this anymore. So now I have a complete free body diagram of the wire showing the forces. I'm looking to see what the failure would be, so I'm looking for sigma yield. And the material I had was yellow brass, annealed yellow brass. And we know that's going to be the axial force divided by the area perpendicular to it. What is the axial force? The axial force is the force in the wire. It's 10,890 newtons. What is the area? It's a wire, so it's circular, so this is going to be pi r squared. We want to find out what the radius is that will just match this yield value. And if you look in the back of the book for the yield value for aluminum yellow brass, sigma yield is 100 megapascals. Shear yield was 60 megapascals. Since this is an axial force, it's going to be normal. So this has to equal 100 times 10 to the 6th newtons per meter squared, because again, I'm going to take it back out of pascals and put it in newtons per meter squared to make sure my units balance out. So I have one equation, one unknown, and when I solve that, I had that radius come out to be 5.9 times 10 to the minus 3 meters. Any questions on the extra credit? Okay. The way I've set up your first exam is it's going to be pretty much drawing free body diagrams, calculating safety concerns, sort of what we've just done with this quiz, and a little bit like we did on the last quiz. I have a couple of choices for how to do the exam. I can spend a little time now reviewing anything you'd like to review. And I could give you the exam right now, go over the exam with you, and have the exam due at 3:15 on Wednesday, 2 days from now. And if I did this, I've already made up the exam, and it's such that you could readily complete it within 2 hours and 45 minutes that we typically have for class time. And so I sort of set this up that if we were here in person, I could have given you this at 12:30 on Wednesday. You'd have plenty of time to complete the exam and turn it in by 3:15. The only difference now being is I would give it to you now. So if you want to spend the extra time on it, that's fine with me, but it is still due Wednesday at 3:15. The alternative is I will give you a heavy take-home quiz, which is more of this, but heavier, I'll just say heavier in calculations and everything, which will be due on Monday. I will go over the quiz with you on Monday, do any final review, and then I will set up for you to take the exam in class on Wednesday of next week. So And
It
if
appears
you,
that people are voting now due Wednesday.
so let me just, I'll give you the opportunity to pick which one you want to do. I'm getting, okay. Is there anybody that wants to have it next week? Speak up. Okay. What I'd like to do now is do a little bit more lecture on this, and then I will send you the exam. I will go over the exam with you, and then I'll still be here tonight till about 6 o'clock or so if you have any questions. What I'm hoping to do is when I'm at the hotel that I'm at in Denver, I'm hoping that I can use their printer to print out your exams that you're going to send me on Wednesday. If I can, I'll print them all out there. I'll have the solution with me. I'll make it up while I'm there. I'll try to grade them while I'm out there, or else the weekend when I come back, so that Monday I would have your graded exams with a written solution to go back to you. If I cannot get the, be able to use the printer at the hotel for whatever reason, sometimes they're very limited on what they'll allow you to print. Sometimes they'll only allow you to print a boarding pass, for example. Then I will have to wait till I get back. And I'll probably print everything out on Monday, grade them the next 2 days, and give them back to you on Wednesday of next week. And I'm hoping I'll be able to print them out at the hotel. At least, even if I can't do that, I can on Monday give you or send you out the solution to the exam. Okay. The only other thing I want to go through very quickly if we go back to plane stress, we said by definition it is equal to an axial force divided by an area that is perpendicular to it. We also said we could use Hooke's law, which says that plane stress is equal to Young's modulus times plane strain. And if we do a little substitution here, if I substitute this back into here, if I divide both sides by E, which is Young's modulus, I have that. If I go back to a definition of what this is deformation in the x direction. If we look at a definition of plane stress, is equal to deformation divided by the original length in that direction. And again, as we mentioned before, this is going to be distance divided by distance. So this could be meters divided by meters, centimeters divided by meters, feet by feet, but this is dimensionless. If I substitute this back into this, multiply each side by the original length, I now have an equation that I can use to find deformation. So if I have a member that is L long to start with in the x direction, This, if I turn it on in, is its cross-sectional area. I put some type of axial force on it. Let's say I put a force like this so that it's in equilibrium. And I know what the material is. Let's use our aluminum 1100. I know that I can find this Young's modulus, modulus elasticity from the tables, and in particular for aluminum 1100, that value is 70 gigapascals, 10 to the 9th newtons per meter squared. So if I gave you a member and I loaded it up, so let's say I started off with this thing being 5 meters long, and it was 4 centimeters by 4 centimeters. I made it aluminum 1100, and I applied 8,000 newtons in tension. I could ask you, what is the final length of my 10-meter beam when I've loaded it like this? We know the final length is going to be the original length plus or minus the deformation, plus or minus dependent upon whether it's in tension or whether it's in compression. Obviously, if it's in tension, it's going to get longer. If it's in compression, it's going to get shorter. And again, we know deformation is equal to FL over AE, where this is the axial force, this is the original length in the x direction, this is the perpendicular area, and this is Young's modulus. So I can put these values that I have in, I will come up with a deformation. This deformation is going to be a length. And if you use a standard metric system, the length is going to come out in meters. So I can take this value, since it's in tension, add it to this. My original length was 5 meters. And it's going to be 5 point something because it's in tension. So you have the ability to find that length. Suppose I had multiple materials. Suppose this is 5 meters. This is 8 meters. This cross-sectional area is 2 by 2 centimeters. This cross-sectional area is 4 by 4 centimeters. This is aluminum 1100. This is aluminum 6061. And let's say I put this system in equilibrium with $12,000 newtons. And I ask you to find out what is the final length of my beam. It's going to be the original length plus or minus the deformation. In this case, the original length is 13. Now I have to come up with deformation. And if you look at this, hopefully what you're seeing is the deformation for the total is going to be what's happening in this first part. And I'm just going to substitute little ones here, where this is beam 1. And then I have to look at what's going on in the second one, which is going to be, again, I'm going to look at what's going on in that region. So if I had 3 or 4 of these in a row, I would have 3 or 4 of these down here that are going to contribute to the total deformation. I find out what that value is, and I can substitute it back in here. So we're going to know the cross-sectional area, because you're typically given it. You're going to know the modulus of elasticities, because I'm telling you what the materials are made out of. You're going to know the length, because that's a physical dimension we had. The forces that we're applying are the axial forces. In this case, they tend to be the same, but you could, just to make sure, do a free body diagram on each section just to see what the force is in that region. You could write it out this way. If you had multiple sections in a row, you could do a summing. You could say this is the sum of where I goes from 1 to however many number that you have. In this case, if I had 2 sections and I use this, I would come up with this.
Professor, we get the value for E from chart, depending on the material.
You get it from this
Okay.
page that I gave you, or I might give you, rather than use these same old ones all the time, I might give you various parameters that I've taken from another textbook. So you're either going to use this page that I gave to you originally, or I'll give you whatever you need. Any questions on this? Reason I did this is going to be your extra credit part for your exam. Okay, you ready to look at the exam? And then we'll go over this and then we'll take a break. Okay, I've just sent you the exam. Once you get it, let me ask you to open it up.
I got it.
Got it.
Okay, let me go over this with you very quickly. And I see that part of my extra credit did not show up on there, so I want to go over that with you too. Okay. I've given you a beam that has a total length of 10 meters. It's attached by a hinge at the wall. It goes out 8 meters. Whoops, scratch that. Let me ask you to forget this one. Okay, for some reason, the exam that I had for you is up on my office computer. It's not down here on the classroom computer. What I just sent you was, had you not decided to do the exam, that was a quiz I was going to give you, a heavier quiz due on Monday. So forget that one. I'm going to go back to my office and send the exam to you, give you a couple of minutes to look at it, give you a break, and we'll meet back here at 5 up. So I will send you the real exam from my office. It's on my office computer. Be back in a minute.